Hi, welcome to the third video in my Proof by Induction Inequality series. In this video, we're going to have a look at an example that is much more difficult than our previous examples. Why is it much more difficult? Well, we're dealing with a choose function. Choose function, historically very difficult to work with, but we're going to use a trick that if we convert the choose function into factorials, it's generally much easier to work with. The reason being is we don't know much about the choose function. Although there's a lot of formulas you can derive and prove, using namely the factorials, we don't know much about it. Whereas the factorials we know quite a lot about. So with this question, we're going to treat it like a normal proof by induction inequality. So we're going to do the base case and assumption. We're then going to do the consideration. We're going to pick a particular side. I'm going to pick the choose function side because I don't want to try target a choose function because it can be generally quite tricky. And then we're going to write our target out. We're going to try and involve our assumption in the consideration. Once we've done that, we're going to use our target and what we currently have to try form a new inequality, which we must prove is always true for n being bigger than or equal to 5. So let's have a go. It sounds a bit complicated, but it'll make more sense when we go. So base case n equals 5. So we're going to have 10 choose 5, which is 252. We're going to have 2 to the power of 8, because 2 times 5 minus 2 is 8, which is 256. So clearly true for base case. Okay, nice. Now we're going to assume that it's true for k, i.e. 2k choose k is less than 2 to the 2k minus 2. So just replacing k up in here. Next, consider n equals k plus 1. So we're going to start with the choose function side. So we have 2k plus 2 choose k plus 1. Now our next step is to try and involve our assumption. So I want to try find this. So what we're going to do is we're going to convert both of them to factorials. So the red one is 2k factorial over k factorial, and then it's 2k minus k factorial, so k factorial again. Whereas the white one is 2k plus 2 factorial over k plus 1 factorial multiplied by 2k plus 2 minus k plus 1 factorial. So again, a k plus 1 factorial. If you're unsure in this formula, search up NCR formula in terms of factorials. You'll find this out there very easily. So I want to try to involve the red function in this white one. So what I'm going to do is on the top, I want a 2k factorial. So I'm going to take out 2k plus 2. I'm going to take out 2k plus 1. And that's going to leave us with a 2k factorial. On the bottom, I'm going to take out a k plus 1 factorial, k plus 1 from the first k plus 1 factorial, and a k plus 1 from the second k plus 1 factorial, so k plus 1 squared. And that will leave us with a k factorial and a k factorial. So in other words, we get 2k plus 2 times 2k plus 1 over k plus 1 squared multiplied by 2k choose k. So we've gone from here to here. Next, we can now use our assumption. So this is less than, well, first of all, actually, I'm going to notice there's a cancellation here. We're going to get a 2 times 2k plus 1 over now just a k plus 1. Notice this is 2 times k plus 1. That's why I've got the cancellation. Now, we've got the less than sign. That's because we've applied our assumption up here. We've applied our assumption up here. So this is less than 2 to the 2k minus 2. And now what's left is we need to try get this to our target. So our target, I'll do this in yellow. Our target is to show that 2k plus 2 choose k plus 1 is less than 2 to the 2k, where I've just got this from subbing in k plus 1 into here. So you can check that you get to the same thing. So we're kind of there, we're almost there. We just need this here to be 2 to the 2k. Now, I've already got 2 to 2k minus 2, so I need to multiply by 2 squared. So I need to show that this here is less than or equal to 2 squared. So let's write this out. So 2 times 2k plus 1 over k plus 1 is less than or equal to 2 squared. We're now going to solve this inequality and find out for what values of k is it true. So dividing both sides by 2 gives us 2k plus 1 over k plus 1 less than or equal to 2. If you remember from my algebra series, we can multiply both sides of a fraction as long as what we're multiplying is positive. Or if it's negative, we swap the sign. But because we're dealing with k being bigger than 5, k plus 1 is bigger than 6. So we're multiplying by a positive number, so it's fine. So we're going to get 2k plus 1 is less than or equal to 2k plus 2. Solving this, well, we just get 1 is less than or equal to 2, which is true. Which means as long as k plus 1 is bigger or equal to 0, because that's what we've used in this step, as long as k plus 1 is bigger or equal to 0, what we've done is valid. So in other words, for all values of k plus 1 being bigger or equal to 0, but k is bigger or equal to 5, so it's true. So we can go back up here, and that's quite a complicated argument. You might want to re-watch that bit. But the main idea is to go from that first step to the second one, we've had to have known that k plus 1 is, first of all, non-zero, because we can't divide by 0. Second of all, that it's positive, because if it isn't positive, the sign would flip. And if the sign flips, we would then have 1 is bigger than or equal to 2, which wouldn't work. That would make no sense. So that's why that works. That's why k plus 1 is bigger than 0. Really, I should say k plus 1 is bigger than 0. But it doesn't particularly matter because k only has to be bigger than or equal to 5. So, yeah. So what we get, rubbing this out, we get that this here is less than or equal to 2 squared times 2 to the 2k minus 2, which is equal to 2 to the 2k. So we've just used our target to get to where we want. So, as true for n equals k plus 1, when true for n equals k, by MI, Mathematical Induction. Again, I'm abbreviating it, but you shouldn't do this if you're doing a test. As true for base case, n equals 5, it must be true for all n greater than or equal to 5. And we're done. Kaboom. Choose function destroyed. But anyway, I hope this video was helpful. Choose function can generally be pretty tricky to deal with, but unless you're a combinatorics master and you know lots of different formulas to do with the choose function, I recommend just converting it to factorials. Generally, once you've got it in factorial form, you can then split it up into being polynomials, and polynomials, well, we know lots about. So that's my recommendation for this. Anyways, thanks for watching, and I will see you in the next video.